Hi everyone, this is Mrs. G, and today we're going to learn how to graph polynomial functions. Alright, so before we get started with graphing, I have a quick warm-up for you, so please pause the video and give it a try, and then hit play when you're ready to check your answer. Alright, so here you can see set up the synthetic division. Make sure you have that placeholder for the missing x term, and make sure this number in the box is positive 1. So since the remainder is not 0, we can say that it is not a factor. So we're going to start off by looking at some graphs of simple polynomials. So those are polynomials that are in the form of a times x to the power of n. So just a single term. So here we have y equals x. So this is just a linear function. We know that makes just a straight line. Here we have y equals x squared, which is a quadratic function. So we know that makes a parabola. So these two you should already know. Then here we have the basic graph of x cubed. So x cubed, if you kind of take this part of the parabola and you flipped it and reflected it, you get that x cubed shape. So it kind of flattens out, but it keeps going up the entire time. X to the fourth looks a lot like x squared. It looks like a parabola, but you'll notice that it's even flatter at the origin than it is for just x squared. And then here's x to the fifth. So you'll notice that x to the fifth looks a lot like x cubed, but again, it's much flatter at the origin than x cubed. So these are the general shapes that these simple polynomials will make. So here are the basic steps to graphing a more complex polynomial function. So your first job is going to be to determine the end behavior of your graph moving to the right. So you want to know what's happening as x approaches positive infinity. So to figure out what's happening going to the right, your job is going to be to look for the lead coefficient. So if your lead coefficient a is positive, then that means that your graph is going to go up. F of x approaches positive infinity. And if your lead coefficient is negative, that means that your graph will go down. F of x approaches negative infinity. So I like to just start by drawing a little arrow either up or down, moving to the right. So once you know what's happening to the right, then we need to determine the end behavior moving to the left, or we need to know what happens as x approaches negative infinity. So to figure this out, we need to look at a different part of our graph. We need to look at the degree. So for the degree, if the degree is even, like 2, 4, 6, etc., then the end behavior is going to match. So if the right side goes up, the left side goes up. If the right side goes down, the left side goes down. So it matches whatever happened on the other side. But if your degree is odd, like a degree of 1 or 3 or 5, etc., your end behavior is opposite. So you simply do the opposite of whatever you did going to the right. So then at this point you'll know what's happening far to the right and far to the left. So we need to know kind of what's going on in between. So that we're going to be determining the x-intercepts, zeros, or roots. So those are all different words for x-intercepts that you might see. So to find the x-intercepts, we do need to make sure that our polynomial is completely factored, and then we just plot those points. And then the last thing we need to do is check for what is called the multiplicity of your zero. So this is going to be a new term for us. So multiplicity is how many times your zero is repeated. So you're really looking for repeated roots. Like if you have x squared, that's a 0 at 0 twice. So this is a double root. Or maybe you have a factor that looks like this, x minus 1 cubed. This is a triple root, or this is a quadruple root. So special things happen to your graph when you have a multiplicity that's higher than 1, so when you have a repeated root. So there's two cases here. If you have an even multiplicity, like a double root or a quadruple root, your graph will touch the x-axis, but it will actually turn around. So it will kind of look like what happens with a parabola. It touches and it turns around. Now, if you have an odd multiplicity, like a triple root, your graph is going to make that shape like with the x cubed function. It will kind of flatten out as it approaches your 0, but then it will keep going in that same direction and it will cross. So you do need to make sure you can show either of these features on your graph. So I know this sounds like a lot, but just keep referencing this list as we go along, and you'll see that graphing polynomial functions is actually pretty easy to do. Okay, let's have a look at example 1. So here we have a function that is in intercept form, or it's in factored form, which is really nice for us. But we have x plus 3, x minus 1, and x minus 4. So the first thing we're going to look at, remember, is the lead coefficient. So the lead coefficient would be any number right here, and really we only care if it's positive or negative. So in this case, you can see that our lead coefficient, we could call it positive 1. So we'll say our lead coefficient is positive. So remember, the lead coefficient tells us what's happening going to the right. So it tells us as x approaches positive infinity, f of x approaches positive infinity. So this says moving to the right, our graph goes up. And again, that's because our lead coefficient is positive. So I'm going to go over here, I'm going to just draw a little arrow facing up so I remember. Okay, next we're going to look at the degree of our function. So we're essentially going to count the powers of x. So I have one power of x here, I have a second power of x here, and I have a third power of x here. It would be x times x times x. So if you were to multiply this out, you would end up with x cubed as your largest degree, x times x times x. So since our degree is odd, remember we really only care if our degree is even or odd. Odd degrees have opposite end behavior. So since this side is going up, I'm going to go down on the other side. Now mathematically, we can say as x approaches negative infinity, f of x approaches negative infinity. So this means moving to the left, our graph goes down. And again, that's because our degree was odd. Odd means opposite end behavior. So now we need to figure out what's going on in between. So we need to figure out where our zeros occur. So just to be really clear, these are factors. X plus 3 is a factor, x minus 1 is a factor, x minus 4 is a factor. We could find the zeros by essentially doing the zero product property for each one. So we could set each factor equal to 0. And this would tell us where our zeros are. So our zeros are going to be at negative 3, positive 1, and positive 4. Now, of course, we don't need to show this every time because the more we do this, you're just going to come to realize that the zeros are always opposite of what you see in the factors. So let's plot those points. So we have negative 3, 0, 1, 0, and 4, 0. And the last thing we need to check for is any special multiplicities because we need to see if there's any special features going on in our graph. So this is just a single root, single root, single root. So there are no special multiplicities. So anytime we just have a normal 0, that means that our graph is just going to go straight through it. So now we just need to find a way to connect the left side to the right side by only crossing our x-axis at the zeros. So again, we can only cross our x-axis at the zeros. So the only possible way to do this is something like this. So we're going to go straight through this way, straight down through this way, and straight through this way. Now, in terms of what's going on in between, so this area right here, and this area right here, we could get a more accurate graph simply by making a t-chart and finding more x values, but this is just a rough sketch of our graph. Also, I want to point out that our y-axis is not drawn to scale. We could really easily find our y-intercept, so let's do that really quick. So remember, our y-intercept happens when x is 0. So we're essentially going to find f of 0. So we do 0 plus 3 times 0 minus 1 times 0 minus 4. So this is positive 3 times negative 1 times negative 4, which is 12. So you can see here that my y-axis is not drawn to scale, so we could just make a point here. We could say that this is at 12. But again, what we're going to be focusing on today is the end behavior and the intercepts, and then any special features of our graph. All right, let's try another one together. So here again, we are in factored form. We have negative x times x minus 2 times x plus 2 squared. So here you'll notice that we have this negative out front, which means our leading coefficient is negative. So this tells us that moving to the right as x approaches positive infinity, our graph is going to go down. F of x is going to approach negative infinity. So again, if your lead coefficient is negative, your graph is ultimately going to end up heading down, going to the right. Now we need to figure out what the degree is. So I'm going to count essentially how many x's we have being multiplied together. So here I have x times x. Now this factor is being squared, so it's x times x times x times x. We count this one twice. So we essentially end up with x to the 4th if we multiplied it out. So our degree is 4. So since our degree is even, remember we really only care if it's even or odd, that means our end behavior matches. So I see this side goes down, so I know that going to the left, it's going to match. It's also going to go down. So mathematically we'd say as x approaches negative infinity, f of x approaches negative infinity. This means moving to the left, our graph goes down. So now we need to figure out what's going on in between. So we need to list our zeros. So when you just have x alone, that actually means that you have a 0 at 0. So don't discount this as a factor. It does tell us where it crosses. This crosses at 0. This crosses at positive 2. Remember, it's the opposite. And this crosses at negative 2. So those are 3 zeros. So 0, positive 2, and negative 2. And then the last thing we need to check for are special multiplicities. So here you can see that we actually have a double root. This 0 has a multiplicity of 2. So negative 2, something special is going to happen. So we say negative 2 has a multiplicity of 2. So remember, if you have an even multiplicity, your graph is actually going to touch the touch the 0, but it's going to turn around. So we need to make sure that at negative 2, we're not actually crossing over. We're going to touch and we're going to turn around. So maybe I'll highlight this point so we remember that something special is happening there. Okay, so now we need to find a way to connect this arrow to this arrow by only crossing at these 3 points. Okay, so let's see. If I go here, remember, I'm starting on the left. Remember, when you approach negative 2, we do need to touch it and turn around because of that multiplicity. But I know that my next opportunity to cross is here at 0, so I do need to make sure my graph turns around and crosses back over somewhere in between like this. And then I have that remaining 0 here, and I do need to eventually reach this arrow going down so I can see my graph is going to turn around and go right through that remaining 0, like this. Okay, so again, whenever you have that even multiplicity, your graph touches but does not cross over. It touches and turns around. Anytime you just have a normal 0, it is going to go straight through like this. All right, let's give this next example a try together as well. So first, let's look at our leading coefficient. You'll notice that it is negative. so that tells us that moving to the right, our graph is going to go down. I'm just going to kind of draw an arrow down here to remind us. And that means as x approaches positive infinity, f of x approaches negative infinity. Again, moving to the right, our graph goes down. Now we need to figure out what's happening on the other side, so we look at the degree. So let's count how many powers of x. Here I see 1, 2, 3, and then 4, 5. So this is an x to the 5th degree. So since our degree is odd, that tells us that our end behavior is going to be opposite. So since this side is going down, this side is actually going to go up. So I'll draw a little arrow there to remind us. So that means that as x approaches negative infinity, f of x approaches positive infinity. So you can see here that the end behavior is opposite. Now let's see where our zeros occur. So we can see that we have a 0 at 0 due to that factor of x. And we also have a 0 at positive 3. Now both of these zeros actually have special multiplicities. You can see that 0 has a multiplicity of 3, so it's a triple root. And positive 3 is a double root, so it has a multiplicity of 2. So here's 0, and here is positive 3. So both of those are going to have something special occur in their graph. So let's see if we can find a way to connect this arrow to this arrow while taking into account these multiplicities. And again, we can only cross our x-axis at these 2 points. So first, let's talk about what happens when we have that multiplicity of 3. So we haven't done an odd multiplicity yet. So for an odd multiplicity, our graph is going to slow down, and it's going to kind of flatten out as we approach the point, but it will continue on through. So it will actually cross over your graph. Alright, so I'm going to do my best to graph this one. Let's have a look. So here, as I approach, my graph is going to slow down. It flattens out as it crosses, but it does continue through like this. So you kind of do your best to make this flattened out curve like this. And now I need to address this multiplicity of 2 for my second 0 at 3. So remember, any double root or even multiplicity, it touches and turns around, so it should not cross over, which makes sense because right now we're below our x-axis and we need to end up below our x-axis, so we shouldn't be crossing back over to the top. So we can kind of pick up where we left off there. It's going to go up, it touches, but it turns around. And that's what it looks like when you have an even multiplicity. So again, odd multiplicities, it slows down and it flattens out, but still crosses. And for your even multiplicities, your graph touches, turns around without crossing. So just do your best when you're graphing to show that you are adding in these features, even if you have to exaggerate them a little bit. Alright, so at this time I'm going to ask you to pause the video and give this problem a try, and when you're ready, hit play and we can check your answers. Alright, so go ahead and check. So here a positive lead coefficient tells us that moving to the right, our graph goes up. An even degree tells us that our end behavior matches. So if the right side goes up, so does the left side. Here we have 4 zeros. We have one at 0, -4, -1, and +2. And we don't have any special multiplicities, which means our graph simply crosses right through all of them. So the only way to cross at these 4 points and to connect your arrows would be to kind of go through and then back up and then down and back up. So something like this. Again, we don't really know at this point what's going on in between your zeros. You could always plug in some x values to get a more accurate graph. This is just a rough sketch. Alright, so I have another one for you to try, so please pause the video again and give it a try on your own. Alright, right, so go ahead and check. Since our leading coefficient is negative, that tells us that moving to the right, our graph goes down. Since our degree, which is 3, is odd, that means that end behavior is opposite. So since moving to the right, I went down, means moving to the left, I'm going to go up. Then we have zeros at -3 and +1, and then you'll notice that -3 is a double root. It has a multiplicity of 2. So we know that means that it should touch and turn around, so it's not actually going to cross. So we could also find that y-intercept here, just so we know where it's crossing our y-axis by substituting x with 0. So our y-intercept is at 9. So notice the scale of my y-axis is not, it's not drawn to scale. So I just kind of marked that this is at 9. So the only way to connect your arrows and only cross at those two intercepts is to actually go down, and then you have to kind of touch and turn around again, and then you go straight through at 1. So again, you cannot cross your x-axis at any other time other than at your zeros. Alright, so the last thing that we're going to do together is we're going to see if we can actually look at a graph and then see if we can come up with an equation for it. So here we're going to create an equation for the functions, and we're just going to assume that our a value is either +1 or -1. So let's have a look at this first graph. So when you're interpreting a graph and you're turning it into a function, the first thing we can do is look at the zeros and turn the zeros into factors. So I see that we have our first zero at -2. So if the zero is at -2, we know the factor is going to be that opposite, x plus 2. So this factor describes this zero. The next zero we see is at the origin at 0, so that has a factor of just x, which we'll place just out front. And then our last zero we can see is at +3, which means the factor would be x minus 3. Then the last thing we're going to need to do is look at that end behavior to determine if our lead coefficient should be positive or negative. So moving to the right, we can see that our graph is going up. So that means that our lead coefficient is positive. So we can just leave it +1. Let's check to see if the degree makes sense. So we have a degree of 1, 2, 3. So our degree is 3, which means it's odd. And you can see that the end behavior is opposite. We also are checking for special features of our graphs. We can see at all the zeros, the lines just go straight through, which means these all have multiplicity of 1. So this is our function. All right, let's look at this next example together. So here, again, let's start by looking at our zeros. So here you can see that we have a 0 at -4, which makes the factor x plus 4. Now you can also see that we have that special feature of our graph touching the graph and turning around. So that actually means that we have a multiplicity that's even. So let's just turn this into x plus 4 squared. If it were x plus 4 to the power 4, it would look a little bit flatter at this point. But again, since it's touching and turning around, we know that that's going to have an even multiplicity. That is a special feature. Then we can follow our graph till we get to our next x-intercept, which is at +3. So that just gives us x minus 3 for our factor. And this just goes straight through, so we know that the multiplicity is 1. And last, let's look at what's happening going to the right. So since our graph is going down, moving to the right, we know that that means our leading coefficient should be negative. So we can just place a negative out front. Here we can see that our degree is 3, 1, 2, 3, which makes sense as to why our end behavior is opposite. So this function describes this graph. All right, let's look at this last example. So here you can see as we followed along, our first intercept comes at 0, so that gives us a factor of x. So you can see here, and this is what I was trying to draw earlier, this graph, it's not just going straight through at 0. You can see that it's actually kind of slowing down, flattens out, but then it does continue through. So whenever you see a feature like that, we have an odd multiplicity. So this is actually would be an x cubed scenario. So again, that was this is what it looks like when we have an odd multiplicity. then follow your graph. And then here you can see that we have our next intercept. This is at 2. So that has the factor of x minus 2. Now this one is going straight through, so it has a multiplicity of 1. Now we need to figure out if our graph should be positive or negative. Since moving to the right, our graph is going down. This is a negative graph, so we need to make our leading coefficient -1. And you can see our degree is 1, 2, 3, 4, which is why our end behavior matches. Any even degree has matching end behavior, just like this. And that is how you can approach looking at a polynomial function and turning it into an equation. All right, so that is all for today's video. Thank you guys for watching.